video I'm gonna talk about ESPRIT algorithm. ESPRIT stands for Estimation Signal Parameters via Rotational Invariant Technique, which is a well-known algorithm to estimate frequencies of complex sinusoids. Previously in this channel, I talked about music algorithm, which is also another algorithm to estimate the frequencies. Both of these algorithms are based on subspace method, but music algorithm is based on noise subspace and ESPRIT algorithm is based on signal subspace. Unlike music algorithm, we doesn't need to search for finding the frequencies in ESPRIT algorithm. Music algorithm is based on noise subspace. ESPRIT is based on signal subspace. Both of them are based on correlation matrix of received signal. R is the correlation matrix and it's M by M matrix. The structure of is like this: A, P, A Hermitian plus sigma 2 IM. IM is an identity matrix M by M. A formed as A omega 1, A omega 2, A omega n. A omega is 1, which is an m by 1 vector. Omega 1, omega 2, and omega n are frequencies. They are unknown and must be estimated. And P is a diagonal matrix, alpha 1 power of 2, and they are the power of each signal in our observed signal. Okay, the structure of the correlation matrix is like this. AP A Hermitian. A is a van der Waals matrix. The rank of A is n, and also the rank of P, because it's a diagonal matrix, the rank of P is n. So the rank of AP A Hermitian equals to n, but the dimension of AP A Hermitian is m by m. So the eigenvalues of AP A Hermitian, actually there are m minus n 0 eigenvalues in APA Hermitian. I can write the eigenvalues of correlation matrix. Lambda of R equals to lambda tilde k plus sigma 2 for I equals to 1 until n. N is the number of frequencies. And and for k equals to n plus 1 until m, we only have sigma 2. If we construct eigenvectors based on the eigenvalues, I can divide subspaces to two subspaces, signal subspaces formed by matrix S, which include eigenvectors corresponding to lambda 1 until lambda n. This is an m by n matrix. And for noise subspaces, the eigenvectors are in G, G1, G2 until Gm minus n. This forms noise subspaces, and this matrix forms signal subspace. Music algorithm is based on G, but ESPRIT algorithm is based on S. The eigenvector and eigen values of S can be written like this: R S equals to S lambda, in which lambda is a diagonal matrix. The entries of the diagonal elements are lambda 1, lambda 2 until lambda n. I substitute R with AP, A Hermitian, plus sigma 2 I, and we will have AP, A Hermitian S equals to S lambda minus sigma 2 I. I can define it as lambda, and we will have S equals to AP A Hermitian S lambda minus 1. And I name this matrix C. C is a n by n non-singular matrix. So we have S equals to AC. That means the range space of S equals to range space of A. The information in A, which are frequencies, are in S. So I try to find frequencies based on the S, matrix S. We use invariation technique. We define two matrices, S1 and S2. S1 is I minus m minus 1, 0. multiplied by S. That means I make a matrix which is S without the last row of S. I mean, I removed the last row of S from the matrix S and remains is S1. And also I define S2 0 I minus 1 S. And this is also the matrix S without the first row of matrix S. These matrices are M minus 1 by N. And also I define two other matrices, A1, A minus 1, 0, A, and A2, A minus A. These two matrices actually, when it's a shift version of each other, this shift appears as changes in phases of the column of A. So these matrices have this relation A2 equals to A1 multiplied by D, where D is a diagonal matrix. Each entries are E minus J omega 1, E minus J omega 2, E minus J omega n, which are our frequencies. And equals to S equals to AC, and this is A2. That means S2 equals to A2C. I can do similar and we will obtain S1 equals to A1C. Now I started with S2. S2 equals to A2C. A2 equals to A1D, and A1 equals to S1 multiplied by C minus 1 dC. I define C minus 1 dC as matrix phi. Phi equals to C inverse dC. Phi and D are similar matrices. That means the eigenvalues of phi equals to eigenvalues of D, which are equals to E minus J omega I equals to 1, 2, and n. If I can find phi, then by finding eigenvalues of phi, we can reach the frequencies. S2 equals to S1 phi. For finding phi, I can find the least squares solution of this relation. Multiplying both sides by S1 Hermitian, and then using inverse of this matrix and multiplying both sides by inverse of this matrix, we have phi equals to S1 Hermitian S1 inverse S1 Hermitian S2. And the eigenvalues of phi, the minus phase of eigenvalues of this matrix give me frequencies. Let's recap our discussion and the ESPRIT algorithm for finding the frequencies of complex sinusoids. First of all, you have to estimate R based on data. If you find the correlation matrix, estimate of correlation matrix, then you should find the eigenvalues and eigenvectors for the n largest eigenvalues of R. And you can form the S based on eigenvectors corresponding to the n largest eigenvalues of correlation matrix, which we call it signal subspace. And then you should form S1 and S2. Both of them can be constructed based on S. S1 is S without the last row, and S2 is the S without the first row. And then we can find phi using this squares algorithm by this relation. Finally, we can find eigenvalues of the correlation, the matrix of phi. And our frequencies are minus phase of lambda I equals to 1 to until n. Thank you for watching this video. I hope you can use the discussion presented in this video.